It's my pleasure to introduce Sylvain Lefebvre. I'm Roberto Scopigno, and it's a pleasure to introduce Sylvain. Sylvain comes from France, from INRIA. From maybe the younger of you who do not know what INRIA is. INRIA is the main research institution in France on ICT, on informatics, and a little bit of mathematics, spread it throughout the countries with different labs. Sylvain did his PhD at INRIA Rhône-Alpes, located in Grenoble, which is one of the best known places for doing 3D graphics, maybe the place in which 3D graphics started in France. And he moved to US in Microsoft Research for a postdoc experience, where he had the pleasure to work with Hughes Hoppe, that most of you probably know. And then after this experience, he was back at INRIA, where he got a permanent position, firstly at Sophia Antipolis and then at Nancy. At Sophia Antipolis, working with George Dretakis, and then in Nancy, where he started this group. The scientific interest of Sylvain span different topics, but the most important activity is focusing on texture processing synthesis, and more recently, procedural content generation. That is the topic of the talk that he will give us today. He is a young researcher, but has already reached a considerable visibility, and his works are rather well known in the domain, and this is demonstrated by the fact that he won in 2010 one of the best awards, the Eurographics Young Researcher Award, which is one of the best together with the ACM Awards. And he is part of many IPCs, SIGGRAPI, Asia, Eurographics, Rendering, Symposium, and others. So thanks a lot.
Thank you very much for the introduction. Okay, so it's a great pleasure to be here attending SIBGRAPI in such a very nice location. So I would like to start by thanking the organizing committee of SIBGRAPI for giving me the opportunity to be here today, giving this talk, and also for the very warm welcome. It's been, I had a really great time so far, and it seems it's going to continue until the end of the conference, so this is great. Okay, so what I'm going to talk about today is focusing on large virtual environments that can be explored interactively. And this is just a fancy way to say video games, right? And so, throughout the introduction, I'm going to use this game as an example in order to describe the challenges we're faced with. This is Skyrim by Bethesda Software, so it's a very recent game from 2011, and you will see that even in such a recent game, we still can see some problems with textures. What you see here on screen is a small part of the map of the game. It's probably 1/5 of the entire map of the game. What's important to realize is each icon that you see here is in fact a full city or a full dungeon that you can explore in great details. And in fact, you can even walk from one location to the next through the forest, along lakes, and along paths. So there's a huge amount of content in this game. And all this content has been created by a team of computer artists and has been manually placed and composed into the game. So it's just a very, very large task that they have to cope with. So we're going to enter this world and go somewhere there. And here you can see a screenshot. It's near a lake somewhere in the game. What you see on the left is the final rendering. And what you see on the right is a wireframe view of the scene. And what's interesting to see here is that the geometry that you can see on the right, it's revealed by the wireframe view. The geometry is in fact very coarse. It's relatively simple. This is especially visible on the floor where you have only a few triangles. And most of the details that you perceive in this image is actually coming from the textures. So for those who are not familiar with the concept, textures are simply images which are mapped onto the triangles so as to give them an interesting appearance. And here you have an example of rock textures. And in fact, nowadays, the textures are not only RGBA colors, it's also normal maps to give some interesting shading information. And those are layers of textures. So in fact, in a single screenshot like this one, there's probably 30 or 40 different textures being used. So it's a huge amount of data. And the issue with that is you have to create this data. So it takes a very long time, of course, for the artist to create it. But then you have to store it somewhere. You have to store it on the DVD, or you have to put them somewhere online, and people have to download it. And if it's too large, then it's going to take hours and hours and hours. And for those who play games such as World of Warcraft, you all know what happens on patch day, right? The server crashes because there's just too much data. And in fact, a lot of this content is are textures. It's probably more than half of the sides of a game, right? And, okay, sorry. So the question is, what can we do about that? Is there a way that we could simplify authoring, but also storage and transfer of the texture content? And in fact, there are solutions which have been proposed very early in computer graphics. You've probably all heard about Perlin noise, and what you see here is a planet, which in fact is a simple sphere, right? So this is the geometry that you have. And what you see is a procedural texture. So this is not an image. It's actually computed on the fly as the sphere is being drawn on screen. This texture is in fact a function which returns a color given a point x, y, z in space, right? And so it replaces storage by computation. So this is perfect for textures. And of course, if you call that in every pixel, you get the final result. So this is great for textures because you do not have an image. You do not have a parametrization. You do not need to compute UV coordinates, which is nice when you have a sphere, right? Because UV coordinates on the sphere is a problem. And also, you have no overdraw. What I mean by that is if you are careful with the way you call this procedure, you can actually make sure that you only call it on pixels which are visible on screen. So you won't waste computations computing the color content for things which are hidden. So this is very nice. Let me describe to you how this is computed, just to give you an idea. Everything starts with a seed, which is a number which is going to determine the final appearance of the texture. From this number, we compute a number of noise layers. So here you have 3 noise layers, and each of these layers is a Perlin noise. So a Perlin noise is a very specific noise which has features only at a given scale. And so here you can see that the top layer has a coarse scale, and then the scale becomes finer and finer. And then what you do is you add a weight to each of these layers, and you sum them together. And you can see that the coarse scale has a weight of 1, and then the weight is divided by 2 every time. And this is a typical way to generate textures which resemble this kind of interesting noise, right? And so this is the sum that you get. And then you feed that into a color map, which is simply taking the gray value from 0 to 1, and you map to a color from the bottom to the top of this color map, and you get a nice planet, right? So of course, it takes some experimentation to do that, but when you get used to it, it's fairly easy. Keep in mind that this is done at every pixel. So these noises are not images, right? It's really at a single pixel that you're going to evaluate these 3 layers of noise, combine them together, go through the color map, and get the final result. And of course, you can play with this, and you can generate other things, so that's, such as this marble vase, which is quite famous. So this is not the original. The original is much better than this one, in fact. But I did my best, right? So, and so, maybe that's it. I mean, this seems to solve all the issues. So maybe 42 is indeed the answer, right? Because we have no texture map. It's easy for authoring. You just have a few parameters, and you get, a large amount of textures. So this is great. But of course, there's a catch. And the catch is procedures are very hard to create. It's very difficult to create a procedure. I mean, we've seen, marble and the planet. Okay, but what about this? How can I write a procedure to generate a field of flowers? How can I write a procedure to generate, this, science fiction type texture, which is very structured? Well, I don't know. And this is why procedural textures are difficult to use. However, the key idea of procedural textures can be used as an inspiration to reduce some of the texture management issues we have on other textures. So before we go further, let's look at what games do, because I showed you these very nice screenshots of this game, and they didn't seem to have any problems with texture. So what am I talking about? Well, most games rely on tilings. And the idea of tilings is very simple. You start from a texture, but this texture has been very carefully created, so that in fact the left edge and the right edge of the textures are exactly the same. And the same is true for the top and bottom edges, which means that if you copy this texture to the left and the right in a regular grid, you cannot see the transitions, right? And this is where the edges would be if you could see them. And the nice thing is that now you have a way to generate an infinite plane of textures. You simply need to repeat. And this is really trivial to do. And in fact, all graphics cards do that. It's a simple GL repeat mode in OpenGL, right? Or the same is true for DirectX. So this is great because now you generate a small texture and you can produce as much texture as you want. Unfortunately, things are not as nice as it seems. This is a screenshot of the same game, and you can be sure that this is a game where very talented artists have been working on this. So they do an amazing job at hiding bad things. Still, if you look carefully, you can see here that this stone is nicely repeating on a grid, right? And maybe it's not that obvious in the foreground. However, in the background, something much worse is happening. I hope you can see that with the projector. I'm going to outline some lines here. And you probably can see these lines repeating in the back. And these lines are not supposed to be here. They are an artifact due to the tiling, which is introducing low-frequency patterns into the image, which should not be there if we had a nice texture map. And so tilings are not so great. In fact, this issue is almost present in any game that you look at today. And so, since they introduced major visual artifacts, we may be wondering why people still use them in 2012. Well, the thing is, they just are a big savings in authoring time and memory, because you create a single tile, and that's all you have to store in memory. So that's why people continue to use that, because it just answers this goal very well. I just want to mention that better tiling method exists, right? So you can do better than what I just showed. So I won't describe this, but just as a side note. Okay. The way I understand tilings are, in fact, as a very first answer to the problem of by-example texture synthesis. The problem statement of by-example texture synthesis is as follows. You're given an example, and you want to generate a large artifact-free texture which is going to look visually similar to your example. So if you're given these images as example, if you do a tiling, this is what you get. But ideally, what we would like to get is this, right? And this looks similar to the small images, but there are no grid artifacts here. And this has been indeed synthesized by an algorithm from the small images you see at the top. So this is what I would like to have. And the thing is, there are algorithms to do that. I encourage you to look at the survey by Wei et al. And there are many offline approaches which are able, they're going to take some time, but they generate these very nice images. The problem is that the output is a big image that, again, you have to store on disk. So it doesn't really answer your problem. It saves authoring time, for sure, but it doesn't do anything for the problem of memory. And because our context is how can you generate these details on the fly, like procedural textures we're doing, this does not answer what we want to do. Okay? And let me give you an idea of the type of things we would like to achieve. Here you have a small example, which is at the top left, and you can see an image which has been synthesized by the algorithm. Conceptually, what we would like to have is an infinite plane of texture on which we could do queries, synthesize this window of texture. So here you have one window, but I could ask for another window, and yet another, so that I generate this entire plane, but I can on demand generate a small part of the texture only. And if these subparts of textures overlap, they should have the same content where they overlap. Why is this useful? Because then you can do things such as this, where you fly over a terrain, and in fact, the terrain here is only synthesized for the small part that you see. There's nothing outside the boundaries. If I was freezing the synthesis, then the terrain would disappear. So this is very useful because it's exactly like with procedural textures. You only have in memory what you currently see on screen. So this is what we would like to be able to achieve. Okay, so what I'm going to talk about next is how you can do that for different types of textures. So we've seen that we can do that for specific textures such as these ones. and we're going to examine other types of textures. And I'm going to start by these textures here, which are basically the ones which you want to map on infinite planes, right? Because they represent materials. Okay, so let's start there. So I call these textures stochastic structures. That's really my own terminology. It's probably not the best, but I needed a name, right? So that's how I named them. One key property of these textures is that they are homogeneous. What I mean by that is if you cut out two windows of textures at different locations, and you look at them, they're going to be similar. So they're visually similar, but also in terms of statistics, histograms, gradients, and so on, they will be similar. What's also interesting about these textures is that they can be locally structured. I mean, you can see some edges and contours, for instance, in the bark texture. But globally, they are not really structured. They're more or less random at a large scale, right? So even though they can be structured locally, they're globally random. And of course, we're going to exploit these properties to design an algorithm. In fact, we already did that, right? And we published an algorithm in 2005 which is able to deal with this kind of textures. And in fact, the terrain you saw, right, the flyover of the terrain, is an example from this paper. Today, I don't want to give you yet again the same algorithm. What I'm going to do is, in fact, to introduce you a simpler algorithm, which is, I think, easier to understand and easier to implement, even though the quality might be a bit lower. And this is actually a SIBGRAPI exclusivity. I never described this algorithm before, so here you go. So this algorithm is a multi-scale algorithm, which means it's synthesizing the texture from a blurred version to a higher resolution and higher resolution version. I'm not going to introduce the details of the multi-scale algorithm, and for clarity, I will stick with the single-scale explanation, but it's really trivial, so I leave it as an exercise to go to the multi-scale version. The idea of this algorithm is to first define a number of layers. So one layer is a tiling of the example, exactly as a naive tiling we've seen before. And even though here I only show 6 tiles, right, you have to imagine this as being covering the infinite plane, right? So it's an infinite tiling of the texture. So we have a first layer, we have a second layer, which is the same, but simply translated by a random offset. And we have a third layer, which is again the same, translated by a different random offset, and so on and so forth. And we typically use 256 numbers, because it's 256 layers, sorry, because it is a nice number, of course. And the way we synthesize the texture is by overlaying a grid of pixels where we want to synthesize the texture. Remember that this is an infinite plane, and I want to synthesize a subpart of this plane. So I'm going to overlay a grid of pixels where I want to synthesize a window of texture. Now, the game is going to be in each pixel to choose one of these layers, right? So that you create the final texture as a little bit like a puzzle, right? By choosing which layer should appear in each pixel. So you may be wondering why, not a single layer is going to be chosen. That's because I'm not going to assume that my texture is toroidal, and I'm going to forbid pixels to show transitions between tiles, right? And that's how synthesis is going to happen. Okay, so of course, when you choose these layers in the pixels, what you want to do is to minimize the error at the transitions between layers so that visually the texture will appear continuous, okay? And this is very similar to some other techniques, like graph cut textures and photomontage have a very similar formulation, even though they don't use this infinite plane thing. But the problem is that because we want to synthesize a subpart of this infinite plane of texture, we cannot rely on the same optimization techniques, which are global optimizers, because of course here global is the infinite plane, so there's just no way, right? So we need something else. And what we do is in fact very simple. You start with a pseudo-random initialization of the choice of layers, and you're going to iteratively improve this choice of layers. The random initialization is pseudo-random because at a given xy coordinate, you're always going to start by choosing the same layer. This will guarantee that when you go back to a specific location, you see the same thing, right? And so we iteratively are going to improve the pixels. How do we improve? We're going to treat all pixels in parallel. It feels well on the GPU, but also it guarantees order independence, right? So all pixels are going to read information from the previous iteration and to output information in the next iteration. For each pixel, we gather a number of candidates, which are, which layer could appear here, and we choose the best candidate to replace the pixel. So we have a small example here at the top right, and we're going to consider the question mark pixel. For this question mark pixel, the candidates are going to be first the neighboring layers. They're good candidates because they may want to grow in this region, and maybe one layer should grow instead of the other, and this is going to be decided. And then we're simply going to give a chance to other layers by randomly selecting a number of other layers. And in a first implementation, you just take uniformly random choice of layers. Okay? And then we need to compute a score for each of these labels in order to keep the best at the end. The score is computed as follows. Let's consider the blue candidate. If we put the blue candidate on the question mark pixel, we can consider the neighbors which are not currently selected as being in the blue layer. You can see that these 3 pixels here are currently selected as being in the green layer, okay? And so we're going to compare the color of these neighbors in the blue layer, which are not currently in the texture, to the color of the currently selected pixels, which are, in this case, in the green layer, right? And if these colors do match very well, then it means that if we choose this pixel, the transition will be invisible. So it's a good choice. If the colors do not match well, we don't want this candidate probably, and we want another one to appear, okay? And this is what we do. We choose the best at the end, and we put it in place of the question mark. And we iterate this process a number of times, typically 4 times per iteration. That's what I currently do. So, of course, this is not a very good optimizer for this kind of problems. It is far from being optimal. However, it is sufficient for stochastic textures for reasons I will explain next, and also it allows us to generate this subpart of textures from the infinite plane. So it really fits our needs. So why does it work? It works because the textures are invariant by translation in terms of appearance. That's why it makes sense to have these randomly translated layers, right? So we exploit this property. It also works because in these textures, if you pick a given location, a given neighborhood, there are many other neighborhoods in the textures which are visually similar. So it is not rare to find a good transition location. This is why this simple algorithm can work. And what we will see is that if we go outside of these assumptions, of course, it's going to fail, right? There's one important thing about subpart synthesis. It's you have to ensure spatial determinism. In order to ensure spatial determinism, you have to think backwards. So let's assume you want to generate a window of 3 by 3 pixels. You're going to consider these pixels as the final iteration of the process, okay? And now we're going to proceed backwards. If you want to synthesize these pixels, you need to know their neighbors at the previous iteration, right? Because remember, in our process, we're looking at the neighbors comparing colors. Now, for synthesizing these pixels at iteration 1, you need to know their neighbors at the previous iteration, right? And once you know the dependency chain to compute the final set of pixels, you can perform synthesis by proceeding in a forward manner, right? Random initialization, improvement. And then you get the final result. Now, if the user requests another window, which is shifted here by 1 pixel, you're going to proceed in the same way, and because the random initialization is a pseudo-random number generator, it's going to make the same choices. So in the overlap region, it's going to match. And because we made sure that all the neighbors were here, all the ones which are useful for synthesis, will have the correct result at the end, right? So this is very important in ensuring spatial determinism. You need to synthesize a bit more than just the final set of pixels. Okay, here are some results in terms of quality. So you can see that it works reasonably well. This is a 512 squared texture from an infinite plane synthesized in 8 milliseconds on a state-of-the-art graphics card. This is a very naive implementation. There's absolutely no time spent in optimizing, so it probably can go faster. Here is another result. And another one, which is a bark texture. So you can see it's fairly reasonable. Yeah, the contrast is a bit low. But. Okay, there are some failure cases. Here is a case where it doesn't work very well. And the reason is that the cracks that you see in the example, there are rare neighborhoods. They're hard to find, right? And because the crack neighborhoods are hard to find, the optimizer locks in the gray region, which is much easier to synthesize. So that's because we're exiting the assumptions we made about the texture. Another terrible failure case is if you take something which is not translation invariant, then nothing nice happens. And this is a problem because these textures are quite common in video games. And this is why I'm now going to introduce a different technique, which is going to address this type of textures, which are highly structured textures, which we cannot deal with the previous algorithm. Okay? Do you have any questions so far? Okay. Okay, so let's go. So these textures are very different, and they're used in a different way as well in games. We call these architectural textures because, you know, facades, and also they tend to be used a lot for architectural environments, indoors things and spaceships and stuff like that. The problem here is a bit different. You no longer really want to synthesize an infinite plane of texture. The problem is more that you have this very nice texture created by an artist, but then you have a variety of surfaces which all have a different size. This could be the facades of different buildings of different height. And you don't really know what to do to, you know, generate textures which would fit exactly these surfaces. I mean, you can scale, right? But it doesn't look really good because the stretching is really heavy. You could crop, but then you're cutting a big part of the texture, and you can see that the borders no longer match what you had in the original texture. And of course, you could ask the artist to create one image per surface, but then it's just going to be a huge amount of texture data. So this we don't want to do. And in fact, the algorithm that I'm going to describe now is not procedural in the sense I described before. It's actually an offline synthesis algorithm, which is fairly fast, but not fast enough to be done during display. However, the algorithm is designed so that its output is very compact in memory. And this compact output can be used directly during rendering by the GPU. So you never have to create a full image when you display the results, right? So that's another way to try to beat the problem of texture data. Okay, what is the key property of these textures that we're going to exploit? The key property is the fact that these textures tend to be auto-similar by translation. What this means is that if you take a window and you move it onto these textures, in this case horizontally, at some intervals you're going to see the same content appear. Not exactly the same, but something very similar. And so we can exploit these as degrees of freedom to create new images from the examples. Of course, we're making an assumption. So again, if this is not true, it's not going to work, right? The way we express these degrees of freedom are not as windows like that. The way we do it is using a parallel path going from the top to the bottom of the image. And these paths, we call them cuts, and they come by pairs, right? So here you can see one pair of parallel cuts, the green and the blue cuts, which are outlined by the triangles. What you can observe is that they are parallel in the sense that they have strictly the same shape. So you can put one on top of the other, and they will exactly match. And they have another property, which is that the colors along them tend to be very similar. So they're not strictly the same, but we hope to create such pairs so that the color differences will be small. And we can measure the quality of a pair of parallel cuts as the sum of color differences from top to bottom, right? And this is what this equation tells us. The exponent 4 is to penalize large differences more than small differences. Okay. Before I continue explaining the algorithm, one important thing to know about it is that the algorithm is in fact working one direction at a time. So if you want to synthesize a new image which has a different height and width, you're in fact going to proceed in two steps. First, you're going to synthesize an image of the right height, and then you're going from this intermediate image to synthesize an image of the right width, okay? So in the following, I'm only going to describe the algorithm for the width, the enlargement or shrink of the width of the image. And of course, it's totally equivalent. You just have to rotate by 90 degrees and it's equivalent. Okay, so let's go back to the parallel cuts. Here is a set of cuts that we extract from the images, just to give you an idea. And you can see that we extract a set of cuts for different spacing between them. In this case, 11, 19, and 58 pixels, but we have all the possible width. Here is how we build the cuts. We start from the example, and we shift it by the offset that we want between the cuts, right? So we have two versions of the example, and now we do an error map, which is the color differences between these two versions. When it's white, there's a large difference. When it's black, the colors are similar. Now we search for the best path in terms of the sum of error along it, so the path with smallest error from the top to the bottom, okay? This path is unique in the error map. However, there are two images, so you have actually two versions of this path, right? And if you go back to the original image, here are the two versions. By construction, they are strictly the same in terms of their shape, but also they have very well matching colors along them. So that's one way to get a nice pairs of cuts. And it's very easy to build an algorithm from this. We iterate over all possible offsets, compute the error map, extract the best cut, flag it as infinite error to extract the second best cut non-intersecting the first one, right? And we iterate this process, okay? And we get a nice set of cuts. It's probably not the only way to get cuts, but these ones work fairly well. Okay, now that I have my cuts, I'm going to describe how we synthesize an image. So I'm going to start by an intuition, and then we're going to build an optimizer for this problem. Here you have 3 versions of the example, it's just for clarity. Okay, so we start with, the idea is that we're actually growing the result. We start from the left column of the image, and then we decide to grow, going from one cut to the next. These cuts are not parallel, they're just different cuts in the image, and we grow from one to the next, simply copying the example. And then at some point, we're going to say, okay, now let's jump, and we're going to jump from this cut to its parallel counterpart in the image. And this is what I do here. And by doing this, I start a new image strip, a new strip of image. And you can see that I switched to the second image, and the jump actually had me go backwards in the example. All right? And then I continue copying, and at some point I decide to jump again, and this time I jump forward to the parallel cut, and I continue copying, which finishes the synthesis when I reach the right border. Okay? And if you look at what happened, I actually built a new image made of 3 different strips. And because I jumped at parallel cuts, I can very easily close the gap to create a final image. And if I chose my jumps wisely, which means with nice matches of colors along the cuts, you actually cannot see the jumps in the result. All right? So how can we use this process and build an optimizer for it? Because I would like to produce the best possible images, not just some random image like that. We made essentially 2 operations. One was to start a new strip. These are the red operations. And one was to grow the current strip and to go a bit further by copying from the example, which are the green operations. And in fact, you can express this in a graph where the edges are telling whether you should grow or whether you should jump to start a new image strip. And this graph is actually going to describe the graph of all the possible images, all the images that can be synthesized, and any path in this graph is going to describe an image. And the nice thing about it is that then by searching different paths, we're going to be able to synthesize different images. So how do you define this graph? The graph is defined on the output, the result. Every node of the graph is a cut from the example at a given position in the output, right? So this is node Cx, which is cut C at position X in the output. Now, we have 2 types of operation, growth and start. For the growth operation, we have edges which are going to go from a node Cx to a node Fx plus W, where F is a cut which is located after C in the source image, right? And where W is a spacing between the cuts in the image. Remember, this growth edge, what it does is copying a part of the example into the output. Right? So that's exactly what happens by following this edge. You go from Cx to Fx plus W by copying a part of the original image in the output. The cost of this operation is 0 because you don't introduce any error, you're just copying from the example. Okay? For the start edges, we are going to go from a node Cx to a node C'X, where C' is the parallel counterpart of C in the example. So you're jumping to a different place in the example, but in fact, you don't move in the result because you're just starting a new patch, right? So you make no copies, you just start a new strip in the output. The cost of this operation is, of course, the color matching cost between the 2 cuts. Because if they're well matching, it's a nice operation to do. If they're not well matching, you probably don't want to do that. And so now that we have defined the graph and the cost, every path in this graph has a cost which directly tells you the quality of the output. Which means that if you want to synthesize an image of width W, which starts and ends by the first and last column of the image, you could choose any other columns, you actually want to go from node S0 to node EW in the initial graph. And to do that, you can simply use Dijkstra, right, in this graph that we just defined, and this is actually going to synthesize an image because it directly optimizes for the cost. What's really nice about this is the result is entirely defined by the path, which is just a series of cuts at a given position. And that's the only thing you need to define the result. So you don't need to store the image, you only need to store the path. And you can actually very easily, from a pixel shader, knowing, I want the pixel at this location, you can easily locate yourself in the set of cuts and find the color in the example. So that's how we're able to reconstruct during rendering. Okay, let's look at some images. Here you see the example in the pink square. And in the middle, you have one synthesis instance. And on the right, you can see the cuts which have been used both vertically and horizontally to generate this result. What's interesting here is that our algorithm is a low-level algorithm. It has no knowledge that this is a facade. It doesn't know anything about the image, right? And nonetheless, it's able to do something which is quite reasonable. In particular, you can see that it nicely deals with the tree, and it would be very hard to deal with such an occluder if you were explicitly looking for a facade, right? And also the nice thing is that because it doesn't know this is a facade, it can do other things than facades, such as the science fiction door. And here, it's particularly interesting to see that the bottom, the left and right, are preserved compared to the example. So, of course, this is not perfect, but I think it really carries the intent of the artist, and this is so much nicer than a cropping or a scaling for very little cost in the end, right? So there's really, well, I mean, that's me saying that, but I think there's no reason not to use it, right? And here is another example of a facade. All right, and here you can see a city where every facade of every building is synthesized from a small set of facades, or 4 of them, and you can see the cuts which are used. And this all fits in 70 megabytes of memory on the GPU instead of 7 gigabytes if we were to store the result images directly. Right, so this is much more compact. And also, we can constrain the paths to obey some user-defined constraints. So for instance, here the user is moving where the door should appear in the result. And by simply constraining where the path has to go through the graph, you can generate only images which are following these constraints. It's a very simple modification of the Dijkstra algorithm. So there are some limitations because, of course, not all textures are nicely, have nice translational symmetries. And for instance, this texture here in the vertical direction, even though it looks like it should work, right, it doesn't exactly have the same thing because it's shrinking. And what you would like to see is this triangle to, continue grow and so on. And of course, this is not going to happen. So there is room for future work in this respect. Note that there does exist techniques which do image retargeting, which could achieve much nicer result, but again, these techniques, they will output an image, not a compact representation, right? So it's really important to keep this constraint in mind. Okay, any questions on this? No? Okay, so we're going to switch to the next topic. So the last type of textures I'm going to talk about are these ones. When you look at these textures, right, it seems that the first algorithm I described should be able to deal with them because they look very similar. And it's true, right? You could indeed use the other algorithm. But in fact, these textures are a subclass of the other ones for which we can do even better than what I described so far. So what I'm going to describe now is very recent work that we published this year at SIGGRAPH. So the techniques I described until now are data-driven textures in the sense that during synthesis, they have to keep the example, right? They cannot generate an image if they don't have the example in memory. And this means that, in fact, your input data, even though it's a small example, right, it's still a lot of data. And in particular, it's much larger than the code you use for synthesizing. And also, it requires temporary memory. In one case, because you need these neighbors and different iterations, so you need to store that somewhere during synthesis. And in the other case, because you need to store the result of the synthesis. And this is bad news, because if you really have a lot of textures, I mean 10,000 textures, something like that, ultimately, you're going to have a problem. You're going to have, again, memory issues. So it does not scale as much as we would like it to scale. The procedural textures, such as the ones I described at the beginning of the talk, like the Berlin noise and so on, they're much nicer than that because, in fact, they only need a few parameters to generate the texture. And the code, which is roughly the same size as for the data-driven synthesis, is in this case much bigger than the input data. Right? If I'm talking about the size of code versus size of the input data, that's because that's where I put the frontier between both worlds. Because, in fact, the frontier between both is a bit hard to define, right? So my criterion is the size of the input data compared to the size of the code which is generating the texture. And in this case, the procedural textures really need only a few parameters. And also, and this is very important, they need no temporary memory because they work on a per pixel basis. So they can synthesize one pixel, forget about it, go to the next pixel. Right? So this does scale up, and you can have any number of textures in your scene, and this is not going to use much more memory. So this is what we really would like to do. And of course, what I'm going to describe now is that you can actually do this for some specific types of textures. What I'm talking about here is quite different from what I said in the beginning. In the beginning, you had to do some black magic to create your texture. What I'm talking about here is a way to automatically build a procedure which will generate your texture, right? So it's really procedural textures by example, right, for a specific class of textures. So what's specific about these textures? These textures, we name them Gaussian textures for reasons which are better explained in the paper, but the key idea is that they have no clear contours or edges if you look at them. So they may be anisotropic, such as the one at the top, which has these stripes, or they may even be periodic, like this woven pattern at the bottom, but they have no contours or edges. The reason that they have no contour or edges is that because these textures are entirely characterized by their power spectrum. Okay? So here you see an input texture and its power spectrum. The power spectrum is a squared magnitude of the Fourier transform of the image. So you do the FFT, you have a bunch of complex numbers, you take their squared magnitude, and this is the power spectrum, which means basically it's the FFT without the phase, right? And so what I'm saying here is that in fact these textures have no useful information in the phase, okay? And let's verify this. Here on the left you have some input textures, so these are the original. On the right you have the same textures where we did a Fourier transform, we destroyed the phase by using a random phase, and then we did the inverse Fourier transform to go back into the image space. And you can verify that these textures on the right, they still have the same appearance as the texture on the left. They're not strictly the same, of course, the phase has changed, but they still have the same appearance. So the appearance is not destroyed by randomizing the phase, which means they have no useful information in their phase. Of course, this is not true in general. If you take this brick wall thing, I hope you can see it, it's very small. On the right, it's totally destroyed. You can't see any bricks anymore. And that's because phase, of course, has all the information about contours and edges, and this is why I said that these textures have no contours and edges, right? That's one way to understand them. Okay, so why is this helpful? It is helpful because it turns out that in graphics, we played a lot with noise. I mean, there's a lot of work on this. I encourage you to read the survey by Laga et al. On this topic. And noise in graphics is typically random patterns, such as the one you see at the top, where you control the power spectrum that you can see at the bottom. So let's look at a number of noises. This here is what we call an isotropic noise. In fact, Perlin noise is quite similar to that, even though it's not as nicely ring-shaped in the spectrum domain. This noise is isotropic because you can turn it in any direction, and it's going to look the same. And you can see that by looking at the spectral content, because you see that it has the same exact information in terms of energies in the frequency bands in all possible orientations, right? So that's given by this ring. The distance from the center here tells you what is the size of the features. So in the middle, it's basically the average value of the image, and as you go to the outside, it's higher and higher frequencies, right? So if this ring was smaller, you would have actually coarser features in the image. You can also see here that the orientation of the features is strongly related to the spectral content. So noise is quite interesting because in the spatial domain, it looks random. It looks like it has no structure, but in fact, it's very structured in the spectral domain, right? And so what's nice about noise is that we do have methods to procedurally generate noise. And this is why we have some hope to be able to exploit these methods so that we can actually synthesize, by example, the Gaussian textures. Okay, the noise we're going to use is Gabor noise. So this is a noise we introduced in 2009, which is based on sparse convolution. So let me describe this process. Here, so nxy is a noise value at xy in your infinite texture plane. And the way it's computed is by a convolution between a random impulse process. Okay, so what this is just dots weighted randomly between -1 and 1, right? This is what it means. it's a Poisson impulse process. Don't be confused by the term Poisson here. This is not a blue noise. So this is not a Poisson distribution. These are just random points. However, if you take a window and you count the number of dots, right? The number of dots in the window is following what is called the Poisson distribution, which has this shape, whose average is going to be lambda, right? That's what it means. And so you're going to convolve this sparse white noise by a kernel, and we choose the Gabor kernel, and I will explain why next, right? And so what this means, this convolution, is that in fact you place this kernel at centered on each dot, and you multiply the kernel by the weight, and you add them together, right? So it's very simple. And what you get is a noise pattern like this one. So this has very interesting properties. First, you can do it procedurally. The reason why you can do that procedurally is that if you, so I'm going to overlay a grid in texture space. If you want to compute the noise value at a given point, xy, because the kernels have a limited spatial extent, of course Gabor kernels don't have a limited spatial extent, strictly speaking, but we clump them at some small enough value, right? And so if you, because the kernels have a limited spatial extent, it's enough to generate impulses in the vicinity of the point, right? Just in a small number of cells around it, of course, with a pseudo-random number generator, so that the same cell always has the same spread of dots. And now you just have to consider the kernels which are close enough to your point so that they will have an influence, right? So thanks to this locality, you can actually generate the noise procedurally. So that's a first nice property. The second nice property, which is much stronger, is the fact that, so in the spatial domain, this is the noise. Now let's look at what happens in the spectral domain. We have a convolution in the spatial domain. By the convolution theorem, we know that this convolution in the spatial domain will become a multiplication in the spectral domain, right? So we'll have a multiplication between the power spectrum of the kernel and the power spectrum of the sparse white noise, and my goal is to compute the power spectrum of the noise. Okay, sparse white noise, and this is a known fact, has a constant power spectrum. So let's assume the value is 1. It's everywhere. It's 1 everywhere. It's white, basically. Okay? And the kernel has some other power spectrum, and we'll see on the next slide what the power spectrum of the Gabor noise is. But what this means is that the power spectrum of the noise is, in fact, equal to the power spectrum of the kernel. So if you can control the power spectrum of the kernel, you can control the power spectrum of the noise, which is quite nice because we're getting to a very precise control of the power spectrum of the noise. And so the Gabor kernel, here in the spatial domain, on the right in the spectral domain, has this very nice property that its power spectrum is actually made of two symmetric Gaussians, and by changing the parameters of the kernel, that is the frequency of the sine wave and the bandwidth of the Gaussian, which composes the kernel, you can actually move arbitrarily these two Gaussians in the spectral domain. So you have a nice primitive that you can locally put in the spectral domain to put energy in the frequency bands you want. Right? So let's verify what happens to the noise. So this is the noise, which is created with the same Gabor kernel, and you'll see that as we move the parameters in the spectral domain, in fact, I'm showing the FFT here of the noise. Sorry, I'm showing the square magnitude of the FFT, and you can see that it does match the one of the kernel. It's noisy because we're looking at an instance of the noise, whereas what I said about the power spectrum is considering the random generator itself. So in fact, what you see is a multiplication of the filter, the Gabor kernel, by a white noise. Right? This is why it's noisy. Okay? So this is good because we can generate a noise with a very precise content in the spectral domain. How can we use this for, by example, synthesis? We're getting there. There is another property which is very important for application, which is that if you have two noises which are which are independent in terms of statistics, right? You can actually add them up in the spatial domain, and their power spectrum will also add up. So now this means that if you carefully place your Gaussians and you add them together, you get a more complex power spectrum. And what I'm getting at is that you can actually use these Gaussians as a basis for any power spectrum, right? And so if I'm given an input texture, I can compute its discrete power spectrum, and then I can fit a bunch of Gaussians on this power spectrum, and this is a decomposition in terms of Gaussians, and by generating different layers of Gabor noises and adding them together, I have the noise which should match my input texture. That's all. So of course this fitting is not something very easy to do, in particular because you want to Oh, there's an automate advance. Okay. In particular, because you don't want to have too many Gaussians. So we use something called basis profit denoising, which is computing. It's an optimizer in the least square sense, but which is trying to maximize the number of zeros in the solution. Right. I won't go into the details. Everything in the paper, but there's a nice algorithm that you can use for this purpose. Okay. So how many Gaussians do you want? Well, let's take an example. Here at the top, you have the texture, at the bottom, the power spectrum. If I use too few Gaussians, the output is not very similar to the input. You can see that something is missing. If I increase the number of Gaussians, it's starting to get better. And for like 240 Gaussians, in this case, I have a nice, something which starts to really resemble the example. I can add more Gaussians, but then there's really no benefit to do so, because when I add more Gaussians, what happens is that I actually need to encode more parameters. So my texture is becoming less compact because it's more memory to describe it. And also, sorry about this. And also the speed of generating the noise is going to decrease, because the more Gaussians I have, the more layers of noise I have, and so on, right? And what's nice about our algorithm is that, in fact, you do not have to pick the number of Gaussians. You only have to select a precision, and the algorithm will automatically adjust the number of Gaussians depending on this precision, right? That's an important property. Okay, so this works on a variety of textures, and here you can see different textures for which the algorithm is performing well. Again, it's very easy to have textures that do not work if you take something which are not Gaussian textures. But as you can see here, it's already a large variety of textures, okay? So the next slide that really want to come on screen is the fact that we can also edit the textures, because now we have a representation of the spectrum of these textures that is very easy to manipulate, right? So by grouping the Gaussians according to the anisotropy of the texture and so on, we can perform editing very easily. So this lets you combine textures and do various things. You're probably wondering how we do colors, right? I did not explain that. We do colors by treating the color channels independently, which is actually a reasonable assumption when you have Gaussian textures. All details in the paper again. Okay, so I will just let run the editing sessions. You can do like strange things such as duplicating energy bands and changing really some features. It's not. I wouldn't say that it is intuitive, but let's say once you're used to manipulating the power spectrum, it's relatively easy to create new things. Even though translations like that are probably the strangest thing to manipulate. Right? But it does some interesting things. And again, here, everything is evaluated on a per pixel basis, right? So everything is done on the fly, per pixel, exactly like with Perlin noise. It also has some other interesting features, because you can generate Gabor noise directly on surfaces without parametrization and so on and so forth. So it inherits all these very nice properties of the original Gabor noise. All right, so we've seen all the techniques I wanted to show you. And to conclude, I would just like to give you a few words about future work and what remains to be done. I think, quite clearly, what we would like is to have more procedural things, and probably the things to look at is, can you take these textures at the top left and put them in the procedural space? This is not easy, but to be honest, the method I just introduced, it was not easy at all either, right? So I think we're getting there. It's probably there are some barriers that we are starting to see opening, and which let us envision this as a real possibility. Another thing that would be nice to consider is when you have such textures. This is really a bunch of geometry with a bunch of stochastic textures, right? So maybe we could do something about this. There are very nice methods to filter out textures and recover the geometry and so on. So maybe it would be interesting to consider encoding this as truly a bunch of geometry and textures that you can generate procedurally, which would be a form of compression, which would be interesting. Right? There are some works that have been done in this direction, but not so much. I think it's really some promising direction to look at. In all that, keep in mind that we want to do procedural generation during display. If you remove these constraints, everything is very easy, right? If you want to encode a texture at its power spectrum, you just store the power spectrum directly and forget about it, right? So it's hard because we want to do it during display on screen as we draw the objects. If you remove this, all what I talked about make little sense, right? So I would like to acknowledge all the colleagues with whom I worked on that. Of course, this is the work of many people. So Samuel Ornus, Anas Lashram, Ares Laga, Bruno Galland, and George Dretakis, and also the funding agencies. So this concludes the talk, and I'll be happy to answer questions. There's some advertisement at the bottom. So if you know someone, you know, drop me an email. Okay, thank you very much for listening.
Thanks a lot, Sylvain. I think that the talk has been excellent and build up a bridge between computer graphics and image processing, which is also nice due to the focus of this event. Do you have questions?
Thank you, Sylvain, for the very nice talk. I was just wondering, along your presentation, is that in all the textures you're only doing the synthesis in the texture domain. That is, you're not really looking at any kind of geometry, like for the terrain or stuff like this. And then if you have, maybe the game has simple geometry, but if you have some kind of, let's say, more detailed geometry, is it, maybe it's not even necessary, but you think it's a possibility to also to look at the geometry to get the synthesis in, if it's that may help somewhat.
It's so I mean, am I correct that what you're asking about is if you have a complex geometry that supports the texture, you would like the texture to adapt to the geometry?
Yeah, exactly.
Right? Okay. So let me show you something, because of course we did that. And so this is exactly what you're talking about. This is a synthesizer which is able to synthesize through distortions and through discontinuities of the texture atlas charts when you have an arbitrary parameterization for the texture. That's one way you can actually adapt the texture to the geometry. There are other ways you can actually synthesize volume textures. We also did that. You can also generate textures like with Gabor noise. You can directly generate on the surface without parametrization. Right? The idea is because it's local, you can actually project locally the kernels, right, around your evaluation point to do this. Does that answer the question? Okay. And this was real time in 2006. Piece of cake today.
Other questions?
This is just a small thing about when you showed us that little tile with the eagle picture, remember?
Mm-hmm.
And you put that in as a solved thing. But the eagle thing doesn't have the parallel asymmetry that you use in architectural textures.
Oh, you mean this one?
Yeah, with the small eagles, yeah?
Oh, that one.
That's right. It's not quite architectural, this one, right?
Well, actually, it does have some repetition. You know what? We can just have an interactive demo too. Yeah. If I have it, do I have it? Oh, I don't have it. Okay, sorry about that. But it does work reasonably well because, in fact, if you look at it, there's a lot of symmetry at the top and the bottom, and in the wings as well, right? So if you ignore gradient, then the wings become degrees of freedom. They can be matched. Right? Yeah.
Thank you.
Something related, may I ask you a question? Mm-hmm. Something related, I like very much this idea of producing cuts and adding things in order to extend or to shrink architectural things. But there are some components which have a meaning, like the car that you have here, or also the school that you have here. A school with 3 eyes or 4 eyes, it's not plausible. Absolutely. Like a car with 3 or 4 or 5 windows, unless you are in US when they use these long cars. But usually, and another case can be, I've seen the last. I was thinking also to the signs that you have on the shops. So if you have a pharmacy, a written sign, if you replace the writing, has no sense. So do you think it is possible to introduce some understanding of the structure to avoid to replicate things which should not be replicated in order to remain understandable.
Yeah, absolutely. So this is, I mean, this is a very good point and a very good question. So indeed, our intention in this design was to create a low-level synthesizer, which has no prior knowledge of the textures, so that it could be as generic as possible. However, in some cases, like for a facade, for instance, you don't want to break the symmetry of the windows. It doesn't make sense to have the windows disaligned or stuff like that. Because our model is low level, you can add constraints on top of it to help guide the synthesis process. And so we did that for a number of cases, such as, you can say, I don't want these objects to be touched because I know it should not be modified, or I want to generate a texture which maximizes the periodicity so that, you try to keep things regular and so on. So on a per case basis, you can try to guide the synthesizer. The problem, though, in doing that is you're reducing the degrees of freedom, of course, right? So there's a trade-off between if you remove too much, then at some point it's just going to be over-constrained and cannot work anymore. So really our intention was to do something which is better than cropping and scaling and will work, in general, even though sometimes it may indeed do stupid things, such as, breaking regularity or stuff like that. But you can guide it in a number of cases. Yeah. Okay.
Thank you, Sylvain. Your nice and beautiful presentation also.
Thanks.
What do you think about, it's just an intuition, because after the tessellator shader nowadays in the graphic cards, a lot of things are moving back from pixels and fragments again to geometry. So is it possible to have something like a procedural geometry instead of procedural images or procedural textures?
Yes, definitely. I mean, a lot of these ideas can go towards geometry. However, it depends what kind of geometry you're talking about. Because, for instance, the equivalent of a stochastic texture is a stochastic geometry, like, I don't know, maybe a grass field or, pebbles or things like that, right? If you stay within this type of things, this might work. However, when you start to deal with structure, it becomes much more tricky, right? Because of the third dimension and so on. I mean, but this you could definitely do in 3D. There's no reason not to add a third step, to just synthesize in the volume. I suspect, though, that there are some other difficulties, right? Because, I mean, what's hard with geometry is the consistency of what you synthesize. With images, you can hide a lot of bad things, right? With geometry, if you want a watertight model and so on, it's more tricky. But it's definitely a good direction to look forward as well. Yeah, definitely. Oh, also for geometry, I should just say that there are a lot of procedural models which are specialized, like for buildings, trees, and their systems, which are extremely powerful for the class of things they address, right? And there's probably very little hope in competing with them in these areas, right? So that's why you should carefully select what kind of geometry you address with this type of approaches.
Thank you.
Hi. If I understood correctly, in the procedural part, you don't have to say the quality. You have a metric to assess the quality, right? You said you don't have to say the number of Gaussians to get to the.
Yes. So you don't say I want n Gaussians, right?
So you have a metric to stop. So
exactly. Yeah.
Can you comment on that metric?
Yeah. So we use an algorithm which is called FISTA for the basis profit denoising, which has a stopping criterion, which is the difference between your current reconstruction of the power spectrum and your target, right? So you set this threshold, and it's going to stop whenever it has the right threshold, and then you look at the result vector, and you have, like all the non-zero Gaussians are the one you should use.
Right.
At the beginning, all possible Gaussians are here, right? All Gaussians. So we have a discrete number of Gaussians. We quantize the bandwidth of the Gaussians. So for every pixel of the power spectrum, you have a full set of Gaussians of different bandwidth, right? And these are your degrees of freedom. So it's a huge vector of possible Gaussians, and then the algorithm is trying to maximize the number of zeros in the solution vector while reaching the precision threshold that you set, right? And so at the end, we get back this result vector. Everything which is below some value is decided as being 0, and we keep the Gaussians we have. Right? So the threshold is not on the visual quality of the texture, right? Because this we have no clue, I mean, so it's really on the only on the power spectrum.
Yeah, I was wondering the visual quality because if I want, I think you saw like you saw like genes, right? Like.
Yes, actually, this one it's a grayscale version of the gene. Yeah.
Yeah. Because if I want to have different genes for different people, then that will get to the problem where I need a visual metric here.
Well, different genes, it's just you change the random seed and you get a different texture, which looks similar in terms of its frequency content, right? Because here we're fitting in the spectrum. So, I mean, the texture in the spatial domain is different, of course. It's a different instance of the same random generator, right, if you want. And what we learn is the parameters of this random generator, which is its power spectrum. You see what I mean?
Okay, but no faded genes, for example.
No?
Faded genes, like if it's washed.
No, homogeneous material. Well, okay, if you have two materials, right, it's relatively easy to transition. There are actually, I don't remember the reference, but there are some works about this. How do you interpolate between power spectrums and these kind of things? We could use that probably. Yeah.
Okay, thanks.
Okay, thank you very much.